Welcome back. In this class, we are going to talk about the series. If you remember, right, we said that sequences is going to be the essential part of finding the convergence of the series. That's why it is so essential, okay, to know what the series is and then how we can use all the tools we learn to find the convergence of the sequences. Let's look at the series. When we say the series, we mean a sum, an infinite sum. And then we are going to denote in this way. So, sum of the infinitely many numbers can be represented by a sum and the general term. So, I have infinitely many numbers as in the sequences, but this time I'm just adding them. Instead of keeping in a list, I'm going to add them. So, in this notation, we should know an will be called general term, and this is the index, and this is going to be sum notation. And then this part, as you see, right, the sum. We have two problems. We are going to talk about the series. The first problem, are they convergent? Are they convergent? Secondly, if they are convergent, if you say yes to this question, okay, what is the sum? If you say no to this question, okay, we should stop. But if you say yes, okay, we can ask, okay, another question. What is the sum of the series? But answering both questions is not going to be easy task. If you can say, okay, it is convergent, finding the sum is more difficult than the first question. That's why most of the time we're just going to be able to answer, okay, the first part of the question. Let's look at an example, guys. An example would be this. 1 over 2 and minus 1. So I'm wondering if it is, if this is convergent. If it is convergent, right, what is the sum of this series? I don't know anything about, right, the convergence of the series at this point. I don't have any rule, any theorem to use. What I will do, I'm just gonna go ahead and I'm gonna try to write it down the general term elements. Look at that. If I wanna see, okay, the elements of this series, I will use this when n is equal 1. When n is equal 1, the element of this series is gonna be equal 1 over 2 over 0, which is equal 1. When n is equal to 1 over 2 over 1, which is equal 1 over 2. When n is equal to 3, 1 over 2 over 2, which is equal 1 over 4. When n is equal 4, 1 over 2 over 3 is going to be equal 1 over 8. So we can continue, okay, we can keep continuing this way, but I'm going to stop at this point. Since my job is to add them, it is not like, okay, just seeing, okay, where it converges. As you see, it converges to 0 if you take the limit of this sequence. But I don't care, okay, what the sequence is. My problem is about the series. What I mean, when I add this number, okay, what will happen, right? Where it converges. To understand that, of course, I'm gonna need to add all these numbers. So if I try to add these numbers, I need to add, right, element by element. So look at that. A1 is equal 1. I need to add right, the first two elements. A1 plus A2 is equal 1 plus 1 over 2, which is equal 3 over 2. A1 plus A2 plus A3, which is equal 1 plus 1 over 2 plus 1 over 4, which is going to be equal, 7 over 4. Let me add these last part. If I add the first fourth term, it is going to be equal 15 over 8. As far as I see, okay, there is no pattern, right, in the sum. But I can use another, right, magical algebraic tool. So I can write, okay, the first sum in this way, 2 minus 1. If you look at the second sum, I know I can write this one in this way, you see, guys. And the third one can be written in this way. And then the fifth one can be written in this way. You see, there wasn't any pattern, right, in the second column, but look at it. If I prefer to write in this way, which I can write, right, there's a pattern here. Okay, first of all, as you see, this will go, right, until infinite. So I can repeat this process infinitely. And then where I'm gonna reach, as you see, I'm gonna add all these numbers, all these elements of my series, which it is gonna give me the radius series itself. And then look at what I did here, right? Between this sum and in the third column, right, I created a pattern. Sometimes, okay, we're gonna try this technique to get a pattern if it is possible, okay, and then we're gonna give a name for this process. This process is, as you see, right, it is so difficult, but it is the most efficient and the best way to find the convergence or the divergence of the technique. And then we're gonna give it a special name. But as I said, and then if you notice that it is so right cumbersome and it is a mess. Okay, to give a name to this process, I will go ahead and then I will show you something else. If you notice that all these rows, right, they are different than each other. And then can I take in this way, guys? Okay, since these are different numbers, as you see, at the end of the day, 1 I have, right, the 3 over 2, 7 over 4, 15 over 8. These are the different numbers, and then I can think, right, these numbers as a sequence. Please be careful. This time, I'm thinking about the sequence, not the series, right? At the end of the day, look at that. I can get a sequence. So what I'm thinking this. Can I use this sequence? Look at it. I use the red S letters. Can I use this sequence to get the convergence of the series? Let's think about it, right? As you see, if this sequence goes infinite, right? When n goes infinite, so this sequence will give me what? All the numbers, right? The sum of the numbers in my series, as you see, right? So if I take the limit of the sequences, you see what will happen? It will give me, right, the sum of my series, as you see. So I can use this approach. Okay, so let me look at the third column. So I'm trying to improve a technique for this part. You notice that 2 is a constant here, but the number I subtract from 2 is going to be the power of 1 over 2 always. What power is this? If you look at here, look at this one. When n is equal to, I calculated the 1 over 2, which is, it was equal 2 minus 1. So 1 over 2 to 2 minus 1. I can do the same thing here. Look at that. N is equal 3. So 3 minus 1. 4 minus 1. So this is going to be equal to this one, right? At the end of the day, my Sn, the general term of my sequences, can be written in this way. Sn will help me to get right the sum of the my series at any point, or I can express in this way: Sn is equal to right the first n term sum of my series, as you see, right? If you notice that, instead of expressing in this way, I prefer to express right in this way. And I know that right at any step, I'm adding right the first n term together. So I can call right the n term sum. When I add right the first n term sum, I'm going to get these numbers, and then I can express these numbers right in this way. And then look at that. Now I found a special sequences, right, to get the first n term sum. What I said this is, as you see, right, when n goes infinite, Sn will go. So look at now. When n goes infinite, Sn will give me what, guys? Sn will give me my series, right? Do you agree with this? Of course. So when n goes infinite, the first term, n term sum at infinite, right, will be equal to my series. Did you see? This is gonna be my first technique, guys, I'm gonna be using. But using this technique is gonna be so hard most of the times. There are some places we are gonna see in the examples, okay, it will be easy. We are gonna use some algebraic technique. Today you are gonna see that, but most of the times it's not gonna be easy. Okay, what about my example? Sn was equal to, sorry, it was equal 2 minus 1 over 2 and minus 1. So if I take the limit when n goes infinite, you see now, these are sequences, and then we're going to call a special name sum of partial sequences. I'm taking the limit of sequences. That's why we learned the convergence of the sequences. When n goes infinite, this guy will go 0. You will remember, right, from the common, some common limit we use, right, at the end of the sequence section. I gave you some of the rules, 6 rules. One of them, right, one of them was this rule, so I can say that this goes 0. If this goes 0, so look at that. I have just 2 here. The limit of 2 is going to be equal to. Did you see that? Now I found, right, this sum of infinite and many number, which is equal to. I showed that. I proved that. Let me summarize what I did by a definition, guys. So this definition will summarize, okay, what I did, and then all the process, and then we're gonna give this special name to that sequences in this definition. So given a sequence of numbers an, an expression of the form a1 plus a2 a3 an is an infinite series of the number and an is the nth term of the series. As you see, this is my series, right? At the beginning of the class, we use this notation. So now we gave the definition of the series. The sequence Sn defined by the sum of the nth term. S1 is equal A1, S2 is equal A1 plus A2, and so on and so forth. Sn is going to be equal, look at it, A1 plus A2 until up to the An. And then I can use this notation as well to represent what the Sn is. K is equal 1. I can start my index at 1 and look at that. A K is the sequence of partial sum of the series if the sequence of partial sum converges to a limit L, as in the previous example, we say that the series converge and its sum is that number. Did you see that? This definition give me two things. First of all, I have a new concept which I'm going to call from now on, right, the sequence of partial sum. And also it tells me, right, if you take the limit of the sequence of partial sum, that's going to be, right, the sum of your series. So let me summarize, okay, in this way. Sn, right, is going to be called sequence of partial sum or sums. And then secondly, look at that. If I take the limit of this sequence and then show if it converges, that's going to be equal to sum of my series, guys. Okay? This definition answers, right, two questions we asked at the beginning of the class. Is a series convergent? I'll look at that. It says yes. If it is convergent, what's the sum? I'll look at that. If you can find, right, this limit of the partial sum, that limit, right, is going to be also the sum of your series. Perfect. Okay, now we can look at some examples. Okay, we have a couple of examples, okay, type of question we can use this definition, guys. As I mentioned before, finding the sum of series using this technique is not going to be easy. Look at this problem. So the question is same. Is this series convergent? If it is, can you find the sum? Right? We asked the same questions. Okay, as you see, okay, The first tool I learned is this one. There is no other thing, right, where I can use. So I'm going to use this technique, sum of the partial sum. Sum of the partial, sequence of partial sum, sequence of partial sum. To be able to find the sequence of partial sum, as you know, right, Sn is equal A1 plus A2, and I need to find out the first n-term sum. Let me try it. If I use n is equal 1, look at that, n is equal 1, this series, right, this an term will give me what? 1 over 1 times 2 plus. When I use n is equal to, this series will give me 2 over 3. And at the end of the day, right, I will get this one. N is equal n, so n times n plus 1. Then the definition says you need to take the limit of this sequence. But as far as I see, right, this sum will continue until infinite, and then taking the limit of this, okay, is not going to be easy one. You can say that I'll look at that this part, right, this part will go 0, yes, but what are you going to do with the sum, right? Just this term goes 0, but I cannot add, right, these parts to find the limit of Sn. So basically, if I want to use, right, the limit of sequence of partial sum, I need to find different way. To do that, I will use another technique, guys, which is partial fraction. I'm not sure if you learned before at high school, but if you have such an expression, I can factor that expression in this way. A over n plus b over n plus 1. If I can write the left-hand side as in the form of the right-hand side, okay, I can find something different, and then I can take the limit of it. So the main problem here, what the A and then what the B is. To be able to find the A and B, look at that. I'm going to do some algebra. So I can multiply this by n plus 1, and I can multiply this by n to get the same denominator. After multiplying, it is going to be equal to this one, 1 over n times n plus 1, and a times n plus 1 plus b times n, and I have the same expression in the bottom. You see, I can cancel these terms. What I will have left, 1 is equal a times n plus 1 plus b times n. I will continue by grouping the common terms. If you notice that I have the a plus b times n plus a, and then 1 I have on the left-hand side. From this polynomial equation, I can think in this way, right? If you remember from the high, so this is 0 times n. So this term will be equal to this term, and then this term is going to be equal to this term. So a is going to be equal 1, and then a plus b should be equal 0. If a is 1, b should be equal negative 1. Great. Now I found, right, my partial fraction in this way. So I can write this expression with these fractions, 1 over n minus 1 over n plus 1. Why I did this? As you remember, right, I couldn't find the limit of the left-hand side term. But now I'm asking one more time, right? Can I find the limit of the right-hand side? Let me try it, right? So first of all, I'm going to create the partial sequence of partial sums one more time. As n is equal, this time, look at it, I'm just going to try this. When n is equal 1, a1 is equal 1 minus 1 over 2. So when n is equal 1, this is going to be my a1. Since my general term, now instead of this, right, I can use this one, guys. So I showed that they are equal to each other. And then later look at that when n is equal to, it is going to be 1 over 2 minus 1 over 3. This is h. And I'm going to continue so on and so forth. Let me write one more term. 1 over 3 minus 1 over 4. And look at that. The last term is going to be equal to this one, 1 over n minus 1 over n minus 1. I can still take the limit of this one, but I noticed something here, guys. That's why I did the partial fraction, and then partial fractions will help us to cancel all terms. Look at it. I had negative 1 over 2 plus 1 over 2. They will cancel each other. And then I had the negative 1 over 3 plus 1 over 3. They will cancel each other. So on and so forth, guys. So at the end of the day, look at what I will have left. Sn will be equal 1 minus 1 over n plus 1. That's great, right? Now I know I can take the limit of this one. Limit of, right, the sequences. Do I know what is the limit of this part? Yes, right? It is 0. If it is 0, the limit of 1, which is equal 1. Did you see that, guys? I found the sum of my series, since it is the limit of partial sequence, right? Sum of partial sequences. And I know from the definition, the limit of the sum of partial sequences will be equal to sum of series. So it is going to be equal 1. So that's the end of the question.